Recently, Odin Shen asked for my opinion on a physical AI project called OpenPAVE. Specifically, is it possible to improve the AI's performance? The project started life running an enormous 7 billion parameter model on a 128 gigabyte DGX Spark. This provides an excellent, accurate baseline to measure from. For speed, you can see it running with an average latency of around 2 to 4 seconds. This is expected because a 7 billion parameter model can produce sophisticated inference, but at the cost of being very energy intensive. Obviously, this leads to the question, what would a low energy version be capable of? Before we answer that, let's cover the basics. What is OpenPAVE and why is it important? OpenPAVE is a ROS2 control plane with an AI test suite to guarantee accuracy. I was given a GitHub link that had the following: a cloud-free robotics platform, a ROS2 endpoint, an inference node, an intent schema, a control daemon behind a robot adapter, and out of the box, a VLM that was running to capture scene observations and gestures and pass those into a control ingress. OpenPAVE's first demo runs PuppyPie, a quadruped robot on a Raspberry Pi. People are rightly excited by vision language models. After all, they're general purpose chatbots that can see the world, although this comes at a cost. They run slowly and they consume a lot of energy. When I first ran OpenPAVE on an M4 MacBook, it ran very slowly and it felt unresponsive, as if the robot was being stubborn and ignoring my actions. This was very frustrating and possibly dangerous. Why don't we just make the VLM faster? I think that would be most people's instinct. But today, I'm going to explain how I made the user experience fundamentally better by splitting the control plane from observation. Starting out, a typical hand gesture could take from 2 to 4 seconds to capture with Mistral 7B. But our goal is to make that instant. On the Orion 06, and it's absolutely instantaneous. So here you can see it turning, return to home, trot, and stop. I ran about 50 experiments and I was able to get incredible speed gains.
Inspiration for my approach came from cortical column research. It's particularly interesting because scientists have discovered that sensorimotor updates move through space and explore surfaces over time. This can be stored in the computer by adding detail to a knowledge graph. And what's amazing about this is it works in a non-destructive manner.
By radically rethinking what the architecture could be, while paying close attention to the aspiration of the original developer's target user experience, I wrapped all of that in a brand new user interface, a flowchart, and this should help people quickly understand what's actually going on in a complex system. I managed to bring the inference time down so that it works accurately under 1 millisecond of classification work. I used an AI called BlazePalm. I slightly dismantled it and then ran a custom classifier on 21 hand landmarks. I passed 80 different shapes of hands into the classifier, and I trained an AI specifically to be able to classify each of those hands in around maybe 500 microseconds. We have radically overhauled how you input gestures into the robot to make it real time, whilst also having the VLM do its job of being able to describe the scene. That can be seen in the top corner. You have to turn those pixels into image patches and then convert the image patches into tokens, process those tokens, write the description, but we want to do that all without draining the battery.
The project ships with small 256 VLM, and that runs on the Mali GPU using OpenCL around 500 milliseconds. It was the fastest candidate and it was adjudicated against held out footage.
My name's Scott Phillips and thank you very much.